Welcome, everybody. This presentation is attempting to show the real way from data science to data engineering, why the second is the final destination. The former is just a starting point. In a way, the whole idea behind the talk started the day that it was not that many weeks ago. I kind of realized that I was seeing too many job posts, too many articles and posts about data science, and that's it. But data science is the starting point to achieve results, concrete results, and to integrate artificial intelligence, whatever that actually means, into applications. In the end, it's just software. It's software, and it could become smarter software, closer to the problems and able to solve more sophisticated issues, primarily related to two major areas, prediction and classification. So data science is the starting point. Data engineering is the final destination. If the overall pattern is the same that we experienced in centuries of life told and to some extent lived, science shows the way to go, demonstrates what theoretically or conceptually can be done, but then it's engineering through technology that makes things happen and work. So AI, whatever is your definition of it, is nothing different from software. One of my favorite slogans is AI is just software. The people around my circle of friends and colleagues, the few people that trust each other as far as AI is concerned, we have a WhatsApp group called AI is just software. It's just software, but it can become intelligent software, and software that we face and write today, for the most part, is not as intelligent as it should be. So that is essentially the starting point. Now, this frame from a cartoon wants to illustrate what I perceive to be the common vision of a large section of the industry, general industry, about artificial intelligence. The cartoon shows a dog and a man with a very large hot dog, whatever it is, hamburger, whatever it is, that doesn't fit into the door, and they just broke the wall to make the hot dog pass. Okay, it's a cartoon. If we transpose the story told by this frame of a cartoon to artificial intelligence, we're not too far from saying that this is the same when data scientists build a 100-layer neural network without even first trying something simpler, a shallow learning algorithm, maybe in some cases a stupidly simple linear regression algorithm. So when you essentially overkill a fly with a bazooka. What is the lesson, the quick lesson we can grab from this frame? Knowledge of the domain, knowledge of the problem, knowledge of the goals, and step-by-step procedure. Step-by-step, proceeding is the most reasonable. It's common sense in the end, but as Voltaire used to say, common sense is not so common. So are you just looking for something you want to sell as intelligent? Are you aware of the real problem you are called or are just trying to solve? Neural network is a kind of magic wand. Sometimes you need a neural network, but very unlikely you need a very simple neural network. What you have to focus on is the tool that is as right as possible for the job you're trying to accomplish. So definition of the job, definition of the way to solve, to do the job. Let's talk about software. We know that there is a training data set. So this is the central part of this slide is essentially the way we structure, we perceive artificial intelligence. So there is a learning algorithm at the center, a training data set that flows into the learning algorithm, and a computation graph that comes out at the other end. We call this generically machine learning, and there is thinking and there is action. Thinking is the training data set, action is the computational graph. Data on one end, software on the other end. So it's about data and it's about processing software. So now, in the vision that is fairly common these days about implementation of what the marketing calls artificial intelligence and technical marketing calls machine learning, there is a dichotomy, neat dichotomy between what is the company's, the organization, data science thing, this mythical entity, and then just software. So the vision seems to be, we need to have a group of smart people, smart guys who knows Python, who knows how to deal with Keras, TensorFlow, how to maybe do some quick manipulation of data, choosing the right algorithm to turn the data into computational graph. But all this thing is a gray area that in terms of concrete applications becomes sort of a web service that some other software calls. The point is that the problem is, as I say things, is that these two worlds, the data world, the data science world, and then the plain software world, those are distinct. And again, the HTTP, REST, or gRPC API, the technology that connects the two worlds is the missing link that connects the two spaces together. So if something is wrong with the algorithm, oh, the algorithm is fine. The problem is the software. And it's never clear where is the problem. It's like in performance, when you do performance testing. Speed, memory, it's always a trade-off. But the neat dichotomy that keeps teams neatly separated with only a web service to be the connecting link, that is a vision that takes you nowhere. So let's try to rearrange, rethink the whole scenario to see which are concretely the roles, professional roles that actually operate in a machine learning scenario. In this slide, I try to express this by putting anyway an arrow that left to right moves from raw data, which is the basic input to running applications, what users consume in production. Along the way, from left to right, from raw data to applications, we identified three distinct professional roles: the data scientist, the data engineer, the ML, machine learning, deep software developer. I don't expect the role of data scientists and the role of ML developers to be overlapping, but for sure the role of data engineer overlaps with both. And why data engineering is crucial? Because it's the role that guarantees that the raw data is structured and kept over time in the right shape to be processed via software and become productionized applications. Let's dig inside some of this, some more details of the roles that are identified here. The role of data scientist, what we should expect from a data scientist, and put it down in terms of jobs. When we decide to hire a data scientist, what can we really expect? Or put another way, which kind of needs we need to identify that can be solved trying to hire a data scientist? Which skills form the role of a data scientist? Okay, the data scientist uses techniques borrowed from both mathematics and statistics to develop the ability to view through the raw data made available. And we expect from a data scientist reasonable guesses about what the data can be turned to. Imagine a sculptor, a painter. Maybe the sculptor gives better the idea. In front of a block of marble, a cube of marble, and he has to take out of it the shape in the marble. I mean, legend says that Michelangelo was able to view through a beautiful, huge block of white marble from Tuscany, from the Tuscany mountains, when he saw that, oh wow, I had the feeling that I could see within that block the David statue that all the world knows. So it's similar the way in which data scientists should approach the mass of data, of raw data they see. They should be able to see through the mass of data and tell as an outcome, as a deliverable, give us as a deliverable what we can learn, what we can take out of the data. So the data scientist should tell the company what they can learn from the data available and which artifacts, and in some cases even which physical products can be planned and for which purposes. For this part, the role of the data scientist configures as a role not completely avulse from the core business of the company. Again, domain knowledge. How can you guess what you can do with your data if you don't know, if you are not deep inside the domain in which the company, the client, if you're a consultant, operates? Domain knowledge is crucial. I like to compare these aspects of the data scientist's role to that of a product owner. The data is the product. What we can do with the data, how can we evolve the data to build new business opportunities, if not final products. So a data scientist needs to be fluent in abstract mathematics. That's the foundation of the job, foundation of the role. But without a clear business focus, it would be hard to see substance. This reminds me a little episode that I faced maybe 2.5 years ago when I was working in the energy industry. One day I was going to a meeting in a huge building of a large energy utility, and when I was doing my own procedures to get a badge and get into the building, next to me, a flow of people vaguely resembling hippies just checked in, regular employees of the company. And someone in my group commented, "Oh, those are the data scientists. This is we are checking in at the same time as data scientists." There were a group of 10, 15 people moving together as a single mass of humans, treated in this large company as special beasts. Okay, they had a space, they had a room, they had an area, reserved area to just think and make sense of the enormous, huge, humongous mass of data that an energy utility can produce and can manage. I was curious to understand the domain knowledge of these guys. Maybe they were excellent in the domain, I don't know. But I mean, being extremely smart in mathematics makes you powerful, but without control, power without control is nothing. I think this was an advertising of some car. Power of mathematics, but the control exercised by knowledge of the business domain. So more concretely, what could be the desired outcome of a good team of data scientists? Given a problem, I would say a runnable model that is much closer to a prototype of a proof of concept rather than a production-ready product. This is the sore point. You cannot realistically expect from data scientists alone something that can be used in production. The point here is not much the quality of the algorithm, but what surrounds the machinery of the algorithm, and that can be fully and smoothly integrated with software applications. So again, when should you consider seriously hiring a team of pure data scientists? If you are a large organization, if you're part of a large organization, an energy utility, a financial institution, a manufacturing firm, an insurance company, or maybe a betting company, a media company, you're large enough to make an investment on people that can just tell you what you can do with the data, and by themselves, or talking and working closely with a technical marketing team, can bring to the table of executives options on how to evolve the business. So for large organizations where the budget is big enough, having a team of data scientists is definitely an investment. But you have to think of that as, I spend this money on an yearly basis just to have a bunch of people think, and that's it. Just think. And when you have thought enough, when you think out of your thinking, you have produced something concrete, you come and we discuss those ideas and try to turn them into product and business opportunities. But this is if you can afford a budget for potentially nothing concrete. Let's talk about smaller companies, which are by far the majority, with significantly more limited budgets. You need products. Okay, which products, which technical artificial intelligence details, those are probably aspects which are anyway needed, but probably buying these services from the outside via consulting can be cheaper than bringing those people inside. So I always wonder when I see we want to hire, we're looking for data scientists. When I see this kind of job posts, if I see this from a bank, a financial institution, a media company, I tend not to be skeptical, but I'm seriously skeptical about the vision of the company itself when I read this kind of job posts from smaller, sometimes just really small, not just smaller, but small, absolutely small companies. So does anybody need a team of data scientists? This is the question, in light of the definition of the role of data scientists that I just shared. In history, investing on what we can call today a team of data scientists has been common, but was done by kingdoms. You remember, no? America was discovered out of the money of the Kingdom of Spain, and the Kingdom of Portugal, more or less at the same time, was doing the same. There was a concrete issue. We want to reach out India, and we want to do that because of commercial opportunities. But moving eastward towards India, which was a proven way to go, posed a number of issues in terms of costs, in terms of constraints. So in front of the possibility to reach India going westward, that was a challenge, not for a small company, of course, but a challenge for a kingdom. That's the way in which, in history, Columbus discovered America. Kingdoms in history used to support expeditions in unknown territories. Think of the British Empire, which discovered Australia and colonized Australia and built the Commonwealth area out of that. Think of the Kingdom of Portugal in the Renaissance time. Think of the Spanish kingdom in the same time. Think of individuals like Magellan, like Columbus. Try to discover, just there, do ease your money, spend the money, go out, explore, and report what you found out. This is the vision that should be used today to practice data science. Now, let's talk about the data engineer, which is a role that is, in my opinion, much closer to reality, and much more common need for companies to hire. And it's a role that technically is, well, significantly different from the role of data science. We don't expect from a data engineer deep knowledge of mathematics, abstract mathematics. But we need this professional figure to be able to manipulate databases, any sort of database. Take care of the discovery of the most appropriate format to store the data. So how to move raw data into an organized warehouse, from data lake to data warehouse. What kind of transformation is ideal for the model that was devised by the data scientists to work, and how to automate the transformation of data to trigger in action in production environments, the model. But this is also feedback back to the data scientist team to revision, revise, rework, rethink the algorithm and then the trained model. How is the performance live? Okay, we have a beautiful algorithm, but it takes ages to give a response. Is this time taken for calculating the computational graph small enough to be acceptable in a live environment? How often the model needs to be retrained to go smoothly hand in hand with live environments? When you train a model and you put the model in production, is a situation very similar to when you go to the driving school and get your driving license. You've been trained. You have been trained on a number of fixed scenarios, close enough to real life, but not real life. The moment in which you put in the car with your dazzling new driving license and start driving in production, the only thing you know is what you have learned. Now, as a human, the more you drive, the more you learn. You train yourself as you drive, but that's for humans. This has to be coded for AI models. Because every time you call the web service that packages the beautiful algorithm, the beautiful neural network, it always has you driving for the first time. There is no continuous learning, or rather, continuous learning is possible. That's part of what is called ML ops, but that has to be coded. And this requires skills in terms of cloud computing, cloud knowledge of cloud environments, knowledge of databases. It's closer to the role of a DevOps or a software engineer than closer to an expert in statistics, in mathematics, in abstract algebra, whatever it is. That's why data engineer, it's data expert, but an engineer, not a scientist. So when you act as a data scientist on data, you work typically on sparse files, mostly CSV, DSV files, static data. You probably rearrange, reshape this data for your purposes, but you do that out of a Python script most of the time. And your goal, declared goal, is probing an idea. But then the next step is bringing this to the next level to make this run and produce business on top. So you need a robust infrastructure made of databases, whether relational, SQL, graph, or whatever it is. You need queries. You need understanding of how databases work. You cannot run on top of CSV files. Or maybe yes, but there is a layer, an entire layer of automation, data processing, a creation and maintenance of a data processing pipeline that goes well beyond Python and much in-depth into classic databases and classic programming. In substance, we are talking about extract, transform, load pipelines, ETL pipelines. Data science focuses on static samples of data which are representative of the business domain, and the more they are representative, the better is can be expected to be the final trained model. But companies to make business, to improve the business through more intelligent software, they need to have applications that drive dynamic live data through the model, and an overall infrastructure scalable enough to support real-world workloads. Another aspect that we cannot afford forgetting is, okay, we train the model. We train the model using sample data, but there is no guarantee that the sample data are really aligned with live data. Maybe we believe they are aligned, or maybe live data, because they're live, change over time, which makes the responses we get from the trained model subject to larger and larger errors. Then we need to retrain. But needing to retrain means what exactly? We stop the application for the time it takes to reconsider a new algorithm, change parameters on the neural network, retest the neural network, retrain the model, which may take days, and then we go to production. The challenge of an effective extractive transformer load pipeline is engineering the effort that brings from training data to production, going through the steps of retraining the model, retesting the model, and maybe in some cases just auto update of some parameters. So in the end, a plain data scientist as a role is not enough at all and won't solve effectively, at least, any real world problem. This is the payload of the key payload, the key takeaway actually of this talk. But now let's let me open up a little bit of a parenthesis to say, okay, I tried to speak as much as possible about roles, trying to avoid the term professional. So let me clarify. A role, what I define a role is the set of skills that an individual is expected to have in a given business context. A professional is an individual that has enough skills to cover a given role. So a role is a list of skills. A professional is an individual holding some of those skills. The same individual may be able to cover multiple roles in a company, or may grow over time to be able to cover multiple roles. So I'm not necessarily saying that you have to hire 3 people instead of 1. But you need to be sure that the people you have, 2, 3, 4, 5, 10, are able to cover 3 roles: data scientist, data engineer, ML engineer. ML engineers. It's a software developer with some specific skills in machine learning. Specific skills in machine learning means something that makes them able to have an interaction with a data science team and data engineers. Because the ML engineer is the team, the person, the individual, is the role, more in abstract terms, that is there just trying to finalize things, to having things done. So I expect an ML engineer to be familiar with machine learning frameworks, so whether they are Python based or .NET based. And they should be also familiar with what it means to set up an ML pipeline. So the training part, the algorithms, the classes of algorithms, the concepts of error, the measures of errors, data manipulation. But they also should be able to put all these things together in terms of via software. So they must be able to write good software, applying best practice like object orientation, DI, unit testing, using powerful modern languages, C#, Java, Go, Rust, whatever, and comfortable with API endpoints, gRPC, REST, web services, and performance-related issues. So, trying to summarize the content of the talk, and moving it in terms of okay, description of the knowledge. I have the feeling that as far as machine learning and AI are concerned, there is a sort of preference, and this is what I perceive from job posts, HR talks, recruiters talks, that there's a research for T-shaped kind of knowledge instead of Y-shaped kind of knowledge. By T-shaped knowledge, typically it's meant being deep vertical in one area, the leg of the T, and having a flat basic knowledge of a number of other side areas. So I know just the basics of a number of areas, and I'm vertical in one specific area, whether it's a neural network, maybe Keras, maybe TensorFlow, this or that. Y-shaped instead means being deep vertical in one area. So the ability to reach heights of knowledge in one particular area, the half leg of the Y, but at the same time, there are, on a smaller number of areas, there is a level of knowledge that is high enough, much more than just basic knowledge. This is the change of paradigm in approaching AI that the point I want to make. So if I need just a T-leg, being a data scientist that knows just a little bit about software, and I'm done. At that point, I have an endpoint, a web service, and it's just a matter of software. My vision is that it's much better to have a team of people with a Y-shaped knowledge that adds the reaches heights, maybe in data science, maybe in engineering, maybe in software, but knows enough of algorithms, enough of pipelines, enough of ETL pipelines. So again, at a glance, what is an ML engineer or an ML developer? His core responsibility is physically incorporating an externally trained model into a client application and supervising the building and the training of the model based on specs. It's unrealistic to think you can hire a data scientist and you're done. You still need people that write software that knows more than just calling a web service. If the web service wraps up a neural network or something. Also because in general, what most companies try to sell as it's done. You have only to integrate in your software. Just call our AI cognitive services, or whatever is the name. Most of the time you get a half-done product. Generic enough to be customized, but still in the need of customization. So the real model you can think of incorporating in the application is more often than not the concatenation of multiple pieces. It's a huge box inside of which multiple neural networks, maybe neural networks and algorithms interoperate. It's never a single piece of AI. And to find the right way to connect these pieces together, you need a team that knows how to engineer data, how to choose and configure algorithms, and also you need software experts. These three roles for a perfect AI team. And now, this is a .NET conference. Let's talk a little bit about ML.NET. When ML.NET came out a couple of years ago, in the beginning, I mean, the first previews, most people approached it as, okay, this is the Python version, the Microsoft version of Python scikit-learns. Oh, they don't even have a neural network, so that is not good. Yeah, Python, TensorFlow, Keras, that's it. ML.NET is just a piece of some bad words of your choice. When I started working on a machine learning book, Introduction Machine Learning, which is a book that tries to give you the mathematical sense of machine learning rather than the coding perspective of it. We had a very frequent friction with some guys on the ML.NET team, because they were in a way fighting our mathematics-oriented approach to presenting machine learning. And they were saying, what we're doing with ML.NET is not copycatting Python libraries for .NET, which is anyway a good thing. But we're trying to make easier for developers to integrate into their .NET applications intelligence. And then in the discussions we had, I learned a number of things. I learned about the relevance of the data loading pipeline, data processing pipeline, training and testing pipeline, and finally, integration and encapsulation in the client infrastructure. If you look at the algorithm in the scikit-learn library, very, very popular and wonderful library for Python, the data flows only through CSV and memory. Can you manage 2 GB files? Well, you can, but you need to have enough memory. If you do that on Azure, you spend on Azure or on a cloud infrastructure, you need to pay a lot of money. The same data can be stored in a database. In real life, the data is often stored in a database. And ML.NET provides, for example, a cursor-based mechanism to read through data, which allows them to happily manage up to 1 terabyte of data on a regular PC. That's because ML.NET, more than just being a collection of algorithms, is a framework designed to be helpful to data engineers and ML engineers. ML.NET is not a tool for data scientists, but it's a tool that helps, that was good or bad, that you consider that. It's a tool specifically designed to help integrating machine learning solutions inside of existing or new plain .NET applications. So this is the perspective I recommend you take when it comes to ML.NET. Don't look at it as just the .NET version of Python, but as a tool for new professional roles like data engineers and ML engineers. In history and in AI, to finish up and conclude the presentation, in history and in AI, science proves something as possible, engineering productionizes it, data science proves something as possible to achieve, data engineering makes it production ready. No magic, no bullshits. That's it. I think that I'm pretty much on time. Any questions?
It's clockwork, Dino. Right on time, to the second. Thank you very much. Yeah, really interesting. Yeah, I was thinking when you started describing the two roles, data scientist and data engineer, I wanted to ask, all right, but should also be some overlap, right? When this roles or these people are working hand in hand. And then when you brought up the T-shaped individuals, then it's probably we're on the same page.
Yeah. No, but I mean, it's it was a sort of reaction to the perception that you have if you look for job posts, if you look at the posts from companies that claim for marketing purposes they want to do, they're doing AI and whatever, but they look confused to me in how to organize things, because okay, data science is a necessary thing to have, but it's mostly it's a preliminary step. What data I have? I mean, imagine you are an energy utility. You have million data coming from wind turbines, from solar panels, from consumption. And now what?
Yeah, indeed, and you need multiple roles to what I call making it real in the end.
Okay, and once you have found out what you want to achieve, what is the job you want to do, then you have to build the thing.
Yeah.
Data science, by definition, proves something is possible. But let me bring it back to science. In the 19th century, Michael Faraday, my hero, proved the relationship between electromagnetism and electricity. He proved that. He showed that was happening. But if today we can cook on induction kitchens, you know, it's because of the principle he discovered. But it took engineering to build the mechanism that uses magnets and electricity to cook your stuff, your pasta, your meat, whatever it is, on modern kitchens. It's the same here.
Totally agree, and it's also I think it's a feedback loop, because you have data scientists that actually, I think you were really on point. It's sort of a similarity to the product owner role, or they should be in touch with other business stakeholders and deciding what sort of information does the company need and what information can be gathered from the data, and then how to fill any gaps that are there. And then while that is brought, let's say, into the operational space, then you need to go back and see it's exactly what we need, and we can take the right information. How do we bring up new data into our models? How do we retrain and so on?
That's about having an entire set of skills and roles, like starting with the storyteller who understands the business problem, and then discussing with the data scientist who plays with the data using languages such as, I don't know, R or Python or whatever. Then you've got the machine learning engineers, and then you've got the the infrastructure engineers. That's kind of the how I see it. And it's interesting how you put together all these roles to collaborate.
Absolutely. And again, even though this could be taken as a talk against the data science, that's not absolutely not the point, because well, let me try to summarize a discussion we had 3 days, Monday, so 2 days ago, with a huge company. So basically, the point of the discussion was what we can do with AI in this business. And they were going towards prediction. We want to have some AI tool that helps us to predict something. But they missed the point that, well, prediction is not so relevant, but monitoring the ongoing of the business was much more relevant. But at the same time, to be able to implement and to think that you can completely turn around the vision, you need to know about special types of neural networks, like, you know, the autoencoders and GANs, competitive neural networks that take the encoder and try to check if the prediction that the neural network does can be validated by another neural network. This is data science. This is specific skills that derive from knowing the state of the art in neural networks, state of the art in algorithms, And it's hardly a type of skills that a software engineer, even though an engineer that knows a lot about ML can figure out. It's another type of skill. So data science is important. The point is, do you really need to hire yourself, if you're a small company, a team of data science, or you can just take this as a service and pay for those services without having the costs inside? But anyway, data science is crucial.
Yeah, definitely. We have a couple of questions from the audience. I think they're mostly about the tools. One is Microsoft Azure ML Studio still used, or is there any way ML.NET going to replace that?
We have never been able to use Microsoft tools, Azure tools as is. Maybe it's us, but that's our experience. For a relatively simple problem like reading the passport. Okay, this problem, reading the passport. I say this because we're going to use this in the next ML.NET book that we're doing these days. So take the problem of uploading on a website the photo, the screenshot of a passport, and extract name of the person. Microsoft claims they have one of the cognitive services, and so if you upload the photo, blah, you kind of once yes, once not, you kind of get some results, but it's not the level of response you need to have when you upload a generic photo that contains a passport. So what we have done is running first a simple neural network that cuts the relevant part from any picture, that rotates and fixes that, and then we use Microsoft to read, once we are able to pass to the cognitive service a properly shaped piece of code, but in the piece of data. So in the end, it's at the moment, I mean, I can only say that it's always a matter of, in first place, understanding that software you have to code artificially to be artificially intelligent, and then that piece of code should be made integrable with the rest of the application. Now, ML.NET, just to speak of a specific framework, is a combination, a collection of tools that tries to make integration, AI existing components with regular code, because it makes so easy to create classes that, from the perspective of client applications, are just classes assemblies you load, and not necessarily web services without latency. So the benefit is that if you find a way to wrap up in an ML.NET package and externally develop, maybe with Keras or TensorFlow neural network, or a basic algorithm, if you don't need a neural network, that you can still code in .NET through ML tasks, that you have a class that can be loaded in process in your application. So ML.NET is about engineering solutions based on ML, and it's the perfect tool for data engineers and for ML engineers. And data science is outside of that.
Correct. Right. Then if you can answer in 1 minute, what's more of a conceptual question, what do you see that's the biggest challenge in adoption of machine learning nowadays?
Finding building the pipeline of ML pieces so that we solve the problem. The passport example, I mean, apparently it's a solved problem. You go, you buy a subscription to AI cognitive service and you're done. No, I wouldn't say not that easily. So you need to understand that probably to have 100% effectiveness from the AI cognitive services, you have to pre-work, you do some preliminary work on the image, which kind of work you need to do, and then organize it. So the challenge is, given the problem, the perfect detailed definition of the problem you want to solve, finding the ML global general pipeline that solves that, which means combination of neural networks, trained algorithms.
Yeah, so basically it's, you need to know what exists out there and have knowledge to combine them.
Yeah, exactly. Yeah. We too many times we are presented the vision that you have a trained model. Okay, what is the model? What's if you open up the hood and look inside? Okay, what I see here? Most of the time, you see a neural network here, another neural network there. The output of this becomes the input of that. You see a pipeline of ML pieces. In some cases, neural networks. In some of certain, I say neural network, but there are 10 different types of neural networks. Recurrent with memory, GAN, whatever. Okay, so combination of them, each taking the output of the other as input, maybe with some basic algorithm or basic data processing pipelines in the middle. So you have a huge box with an input and one output. Defining what goes into the box, that's a challenge.
Definitely.
Well put. All right, Dino, well, thank you very much for being with us, as always.
I think it's just we just triggered yet another conversation. We want to extend the invitation for the next editions to continue that conversations. To me, the talk popped up one of my favorite quotes, which is, predictions are difficult, especially about the future. So, till the next conversation, we'll live with that, okay? Thanks again for being with us at CodeCamp. See you next time.
Thank you, guys. See you next time.
We'll now have like a